from an individual.
Yes.
You're live.
Oh, thank you, Katie.
Hi, Katie.
Yeah, isn't that strong?
Yes. Yes.
Makes sense.
Yeah, I agree. I'm Richard. I've had enough of the whole exam, so pretty happy to be done with the for now at least.
We have a drop in the office. Just drink like this part.
We're going to try.
Fertilized and
Nice. Okay. And of course it doesn't make sense.
of course, I tell you just to worry about the top and then
Option number 1 does not work. We should now try option number 2. You're doing it right.
I am a certified
So there's something else in the top.
Option number 2 works.
I'm another US person.
don't forget to turn off flux.
Turn on what?
Oh, thank you. I will.
For more than an hour, just in case.
Yeah.
Thank you very much.
Until sunrise, that's for more than an hour, right? Here.
Whoa.
Very focused.
This is a bad guy. Let's see. I'm trying to think if I need to. Okay, for this one,
I'll take them.
I
Let's go.
Oh, that's
The result in it.
Ah,
I think you got this. I do 2 lines and they don't line up. That's interesting, yes.
Yeah.
Because they should. Because physics says they should.
Yeah, but they don't.
So something is going on here. There's some real data, there's some real data. And a physical law and says they don't agree.
I bet you
I mean,
depends on
yeah, bro. That's still right. Still tells you something. Most afraid of the physics is correct. but they- You know, yeah. Your group usually is smooth. Yeah, probably. You know, it's all very much. Well, yeah. And there's such a thing as good data. Yeah. It's terrible. One plus or minus 2. Yeah. So we have no idea. So yes, we have error bars on it, like comps, error bars,
So they know, but this is going to be live streaming throughout, so just in terms of audio. Apparently the chairs are the most like noticeable height.
I'm gonna let you music, which is like
Yeah, it's like. Make it landing happy.
I was trying to decide what to come back. But then, Cheryl's, it's like, okay, now I Good.
No, this is not.
Yeah, I don't know. It's crazy. I was like, oh, okay.
I volunteered.
I get things.
We eventually say, you know, about this. In months, one of those.
Right.
Yeah.
Sounds about right. It looked pretty, given that it was only this one.
Yes, in the meeting, like, it was
Right. Good enough. Look at it, be like, yeah, that's not no.
There's some other. I saw your message saying that. Like, you know how bad all these.
Yeah, definitely. Oh, yeah. 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 Yeah, that's right. Right, yeah, we're gonna need to go a little bit beyond that, I think. Yeah, that can't be right. Yeah, I don't know where that came from either. Yeah. Yeah, something.
Well, that's
Right, yeah. One of the ones that we got to.
Wait, early tomorrow. What did you say?
Yeah.
something that helps. Yeah.
So, welcome to our second AST dissertation defense of the summer. Today, Josh is going to be presenting her dissertation on propelling supermassive black holes. So the format of this is that there's a 45-minute presentation and then a little bit of time for questions from the audience. Please hold your questions until the end of the talk. And then after the questions from the audience, then everyone but the committee will be dismissed, and Josh will go into a closed session with the committee. So I think you also say it. Yes.
All right, for those who don't know me, I'm Andy Robinson. I'm Yash's advisor. So what can I say about Yash? Well, turns out quite a lot, but I'll try to keep it short. So Yashashree joined the AST program in 2014 after completing a Bachelor of Science in Astronomy at Ohio University. Over the last few years, she has been analyzing Hubble Space Telescope images to try to track down mobile monsters, which are believed to be the products of the mergers of two supermassive black holes in the centers of galaxies. And she's going to tell us all about that in a moment, but if I had to find one word to describe Yash, it would be multi-talented. Okay, that's two words hyphenated. Multi-talented, because not only is she a monster hunter, she has also pursued a bewildering variety of other activities and interests while she's been here, including dance, Korean culture, calligraphy, and most notably acting. She's performed challenging leading roles in 5 or 6 productions on campus and around the community. And she's also a member of the Playback Theatre Group, which runs workshops on issues of diversity and inclusion. So Yash has been named as one of the 2019 Women Legacy Leaders for RIT, selected from this year's graduating class, and she also won the American Astronomical Society Chambliss Poster Presentation Prize back in at the 2018 winter meeting. So this combination of art and science, I would say Yash embodies the RIT president's ideal students in many ways, but at heart, she's really a big city girl, and sadly, Rochester doesn't quite cut it. So in a few weeks, she's going to be leaving, first to India, and then starting in August, a postdoctoral fellowship at Seoul National University in Korea. So with that, Yash.
Thank you very much, Andy, for the wonderful introduction. So, good afternoon, everyone, and welcome to my dissertation talk, where I shall talk about the gravitational recoil of supermassive black holes in nearby elliptical galaxies, or as I like to call them, my little monsters. So, today I shall first start talking about the introduction and the motivation that leads us to study such recoiling black holes. My dissertation has been split into 2 different projects. The first of which is a search for such recoiling black holes in the nearby universe, in particular using Hubble Space Telescope images. Then I shall talk about my second project, which is on a particular quasar, E1821+643. Beautiful name, isn't it? It's a candidate recoiling black hole, and we have Gemini observations and Hubble Space Telescope observations for this object. And I shall also be talking about some spectroastrometry simulations that we did. I shall then end the talk with a brief summary of all of the conclusions, followed by future prospects for the field. Characterizing the cosmological evolution of supermassive black hole population will be a major focus for current and future NASA missions, as well as the next generation of large telescopes. There is compelling evidence that a supermassive black hole resides at the centers of all large galaxies. Such black holes grow mainly via accreting mass and can be identified as an active galactic nucleus. Dark matter hierarchical simulations also predict the galaxies evolve through gas-rich mergers, which leads to massive starbursts. So when two such large galaxies merge, their two supermassive black holes first form a binary at the center of the merged galaxy. This binary forms via dynamical friction and continues to decay. This decay is also aided by three-body interactions that the binary has with the surrounding stars. Eventually, once the separation of the binary gets small enough, gravitational wave emission takes over, and this is what drives the binary to coalesce. Which brings us to our main topic, gravitational recoil. Here we have our simulation by our very own CCRG, where on the right-hand side panel, we see two generic black holes, which are about to coalesce. On the left panel is the radiation, the gravitational field radiation that is emitted per unit solid angle. As you can see, as the binary is about to coalesce, the gravitational waves that are emitted are anisotropic, which causes the merged black hole to now get a recoil velocity in the opposite direction in order to contain the momentum. So what does the velocity that it gets depend on? Well, there are several factors that go into the kind of velocities that you expect. Some of the most important ones are the orbital and spin configurations of the binary, as well as the mass ratio. Here we have the prediction of the probabilities of the different velocities that you can expect from such a coalescence. As expected, the most highest velocities that you get, which are about a couple thousand kilometers per second, are very rare, and the general ones that you expect are on the order of a few hundred kilometers per second. So once this black hole has a velocity, it starts oscillating back and forth in the gravitational potential of the galaxy. Coulandris and Merritt 2008 named 3 different phases of these oscillations. Phase 1, which are harmonic oscillations, are very short-lived because the oscillations are very quickly damped by dynamical friction. Phase 2 oscillations can have an amplitude of 10 to about 100 parsecs, which is less than phase 1, but this phase can last for about 8 billion years. So during phases 1 and 2, the supermassive black hole appears to be displaced from the center of the galaxy. Eventually, the black hole undergoes Brownian motion as it comes to equilibrium with the surrounding stars. So now that we have established the parameters for a recoiling black hole, how can we identify them? Unfortunately, the gravitational waves that are emitted during the coalescence of such a supermassive black hole binary merger cannot be identified by LIGO. Sadly, pulsar timing arrays have also not yet identified such a recoil. So we have to look into different avenues in order to identify such recoiling supermassive black holes. And the avenue that we turn to are observational evidence in the electromagnetic regime. So if we assume that the supermassive black hole continues to accrete mass after it receives a recoil velocity, it will still appear as an active galactic nucleus and can be identified. Depending on the amount of recoil velocity that it receives, the supermassive black hole will retain the broad line region as well as the accretion disk. In general, the narrow line region and the jet are left behind. The amount of material that stays bound to the black hole is approximately given by this red circle over here. So now, how exactly do we observe these offsets? There are 2 distinct kinds of offsets that we can look for when we're searching for such recoils. The first one is a velocity offset between the broad line and the narrow line emission. As you can see here from the spectra, the narrow line emission is Doppler shifted with respect to the broad line emission. There have been several studies which studied such velocity offsets, including by Rackles et al., which studied about 16,000 galaxies, and Salmanza et al. 2012 has also searched for about 16,000 galaxies and had 32 objects as candidates. The second kind of offset that we look for, and the one that I am most interested in, is a spatial offset, which is an offset between the position of the AGN and the position of the center of the galaxy. Of course, now these offsets need to be large, or they need to be in nearby galaxies in order to be visible to us by the current generation of telescopes available. One of the examples is M87, where Bachelor et al. 2010 noticed about a 15-ish parsec distinction between the position of the black hole and the center of the galaxy. And if you remember, M87 is important for another reason. The first new image of a black hole is from this galaxy. This brings us to my first project, which is finding spatial offsets in nearby elliptical galaxies as a signpost of gravitational recoil. The main motivation for this project comes from the fact that the time between galactic mergers is approximately comparable to the timescale of gravitational recoil, which is about 1 billion years. We also assume that after a merger, after receiving the recoil velocity as well, the supermassive black hole continues to accrete mass and thus it can be identified as an active galactic nucleus. Which is why we expect to see such recoiling black holes even in the nearby universe where galaxies have undergone mergers in the past billion years or so. But what kind of offsets should we expect? So here is Hubble Space Telescope distance for 1 pixel corresponding to its relative redshifts. So here are 2 lines corresponding to the 2 different plate scales that you find with the Hubble Space Telescope instruments. And a distance between the offset between the AGN and the photocenter needs to lie above this line for its corresponding redshift to be able to be identified as a separation of 1 pixel. So, what kind of sample do we look for? Lena et al. 2014 analyzed 14 nearby core elliptical galaxies to see if we can identify spatial offsets in them. As I mentioned before, once a supermassive black hole in the merged galaxy is undergoing a binary orbit, it interacts with stars, 3-body interactions, which leads to excavation of the central region of the galaxy. This causes the light profile, as you can see in the top right plot, to flatten off towards the center. These kind of galaxies are called core elliptical galaxies. Galaxies in which the light profile doesn't flatten but continues to rise towards the center are called power law galaxies. We expect to find gravitational recoil in core elliptical galaxies because, well, that's where the binary formed and eventually coalesces. And we are also looking again for smaller redshifts, so nearby elliptical galaxies within a redshift of 0.3. Now, Davide-Lena sample was very small, only 14 core galaxies, of which he did find 6 robust candidates. So our motivation is to expand this to a much larger sample of nearby elliptical galaxies that have high-resolution images available in the Hubble Legacy Archive. The galaxies that we chose came from a parent sample of 5 different studies which studied radio-selected galaxies in the nearby universe. All of the galaxies in these samples were visually inspected in order to select our final sample because there are several different kinds of galaxies that they observed. And here are a few examples. For the purposes of this study, we did not choose galaxies that are currently undergoing mergers or the ones that have a very strong point source or the ones that have dust structures that cannot be easily masked out and thus obscure the position of the AGN or could interfere in figuring out where the photocenter of the galaxy is. So after weeding out all of these, after weeding out and visually inspecting about 300 galaxies, we've chosen 96 galaxies for our final sample. Now these include both core and power law, not just core like Lena's objects. So we have 51 core and 45 power law galaxies in our final sample. We also conducted follow-up Hubble Space Telescope infrared observations for 5 of the objects that did not have infrared images in the archive. So we go on to our image analysis. Here's a cartoon of an example elliptical galaxy. Here, the contours represent the isophotes of the galaxy, which are then modeled, and a flux-weighted average center is found to denote the photocenter of the galaxy. It is then compared to the position of the supermassive black hole, which is traced by the position of the active galactic nucleus. And we see whether there's an offset or no. Here's a schematic illustration of the analysis for one of our objects, 3C076.1. Here's an optical image for the object in the filter 555 using the Hubble Space Telescope. The top 2 panels show the isophotal analysis conducted to find the photocenter of the galaxy. The top left panel here, you see a similar image like the one that I showed before in the cartoon, where the contours represent the isophotes of the galaxy that are modeled using ellipse. Here, the outer isophote limit is chosen by comparing the signal-to-noise ratio of the galaxy to its surround. The inner isophote, however, is chosen so that the AGN itself does not interfere in the isophotal analysis, as well as if galaxies have nuclear dust planes, as you can see in the residue image, they also do not interfere in the isophotal analysis. The bottom two panels show an unsharp masking process which is used to figure out exactly where the AGN position is. The first is a median smooth image which is then subtracted from the original image. In the residual, the position of the AGN is highlighted by the yellow arrow. So here are the results for the galaxy that I just shown, 3C076.1. The top right panel is again the light profile of the galaxy, and as you can see, it flattens off towards the center, meaning that this is a core elliptical galaxy. The yellow circles here represent the individual isophotal centers for all of the isophotes that were modeled for this galaxy. The red star in each of the plots denote the flux-weighted average center used as the photocenter of the galaxy, whereas the green star is symbolizing the position of the AGN. In this particular case, there is a clear offset between the two positions. On the bottom is just the distribution of the isophotal centers. And here is an example of a null result where you do not see a significant offset between the two positions of the photocenter and the position of the AGN. And this is NGC 4623. So, what about errors, you ask? So there are different kinds of errors that go into this analysis. And because we're looking at two different positions, there are different errors that go into each. The first one is an error on the AGN position. So here is where we took synthetic galaxies that were made using GalFit. We used a couple different galaxies to model them using GalFit. The model of the galaxy was used as the base, as is shown in the leftmost figure. And then we added in the noise for different noise levels, between 0.5 to about 10 times the noise level, as can be seen in the middle plot. A fake point source was also added to serve as the AGN position, which can kind of be seen here. I made it realistic so you can't really see without other stuff. And then we have the ellipse model on this combination of the GalFit model and the residual. We found that adding up to 2 times the residual, so 2 times the original noise level, we can still accurately recover the position of this fake point source that we had introduced. The second kind of error is on the photocenter. As I mentioned before, individual isophotal centers have an error of only up to 1/10 of a pixel, which are represented by the blue histogram here for the X and Y coordinates for a couple different galaxies. To further analyze the compounded effect of all of these errors, we've also conducted similar synthetic galaxies, as I mentioned before in the previous panel. And we also added in the noise level, again, from 0.5 to 2 times the residual to see what kind of effect we can see on the errors. Here, the ellipse error is the error, again, as I said, on the individual isophotes. The true error is now the difference between the GalFit center, which we know because we know exactly where the position is because we introduced it, relative to the ellipse isophotal centers for each individual isophotes in the model on our model, which is shown here in the red. So conservative estimate for the error that was chosen from this analysis was about 0.3 pixels. So to summarize the error analysis, the AGN error is affected mainly by the noise level of the galaxy. It is also affected by the quality of the point source, the intensity of the point source. And if the signal to noise ratio of the point source is approximately equal to that of the galaxy, then the errors can rise. The photocenter position, however, is mainly again affected by the noise level, and a conservative error of 0.3 pixels is chosen as the error. There's another error that comes in, which is isophotal twisting, which you see in a lot of galaxies. So here is an example of a histogram of an x-coordinate of one of the models that we made. And as you can see, this is not a Gaussian because there is isophotal twisting and sometimes a little bit of wandering of the isophotal centers. So in order to account for these errors, we have chosen the interquartile range, which is between the 25th and the 75th percentile of the distribution of the isophotal centers. We compare the displacement that we get to this IQR, the interquartile range, to find out whether or not a displacement is significant. We have chosen 2.4 times the IQR as a high significance displacement because it corresponds approximately to the 3 sigma level if this was a Gaussian. And then the other two, the intermediate and low, correspond to the lower sigma levels. But it is not enough to only analyze one image per object because in case of the object that I showed before, it has a dust lane and it does interfere in the location of the AGN, which is why we have to resort to multi-filter analysis, where at least one image from each optical and infrared be chosen for all of the galaxies in the sample, all 96 galaxies, wherever available, of course, in the legacy archive, and analyzed to see if the displacement is consistent across the different filters. So here are the results for 3C076.1 in the optical and in the infrared, where the dust lane does not affect the location of the photocenter and the AGN as much. Good thing for me, it's consistent. Yay! Now this goes to choosing candidates. So here, this plot shows the distribution of the normalized IQR in X and Y for all of the candidates, for all of the objects, all the 96 objects in all of the images that were used to analyze them. The red filled-in circles here represent the candidates that were chosen. The two lines represent 2.4 times the IQR, which we've chosen as our high threshold, which is approximately the 3 sigma level. So in order to be chosen as a candidate for the first cut, an object would have had to have a significant displacement in at least one X or Y coordinate in at least one image. We found 18 candidates with this first cut, 14 of which were in core elliptical galaxies and only 4 were in power law galaxies. Here are the radial distributions of the offsets that we observed, separated by infrared and optical. Here, the red bars show the core elliptical galaxy displacements, and the blue bars show the power law galaxy displacements. The displacements range from about 2 parsecs to about 830 parsecs. So putting this in context of one of the figures that I had shown you before, here is a comparison of the multi-filter analysis for all of the candidates as a function of redshift, comparing it with the two different plate scales you find with the Hubble Space Telescope instruments that we used. And this is the projected radial displacement now for all of the candidates. As you can see, as expected, only higher displacements are found at larger redshifts because those are the ones that can be identified. For our favorite sample, 3C076.1, here we are comparing the two different images, the two different radial offsets. Here in red is the infrared offset, and in the blue is the optical offset. The red offset is not that affected by the dust lane and hence is more believable as a real offset. The good thing also is that both of these offsets are approximately in the same direction, which leads us to believe more that this is a consistent offset. But apart from just gravitational recoils, there are other mechanisms that could cause these kind of spatial offsets. The first of which are asymmetric jets. If there is an asymmetry in the jet power, over time the acceleration can cause the black hole to have a spatial offset between its original position and between the center of the galaxy. In these cases, you expect to find a tight correlation between the displacement axis and the axis of the jet. Another one is stall binary black holes. In certain circumstances, the binary stalls if there aren't enough stars to undergo three-body interactions with the black hole so that the separation can get low enough for the gravitational wave emission to take over and cause coalescence. In this case, if only the secondary is accreting, for instance, it appears as a recoiling black hole when it is not. And the third is the case of massive perturbers, where perturbers like stellar mass black holes, molecular clouds, or globular clusters can cause a sort of shift between the position of the black hole. So coming back to our favorite object, forgot this doesn't work. Here's the jet. And now you can see approximately the jet axis kind of lines up with the axis of the displacement, which means that jet acceleration is a possible cause for this particular offset. So to summarize all of the conclusions from my first project, out of 18 candidates, 6 were chosen as robust candidates. To be a robust candidate, a candidate should have multiple observations which are consistent with each other in both the optical and the infrared. The displacements for the 6 robust candidates were between 5 and 40 parsecs. Out of the 6, however, 5 of them were core elliptical galaxies, which means that 10% of our core elliptical galaxy sample showed a significant displacement. And only 1 power law galaxy showed significant displacement, which is expected because we expect to find displacements in core ellipticals. Out of the 5 core galaxies, 3C76.1 and 430 have jets which are aligned with the displacement vector, making it a possible cause for the offset. But that's not all. Apart from the 6 candidates that we have, we also found 3 that appear to be dual nuclei. 2 of them have been studied before by Lauer et al. And Lanai et al., where in 4486b and 5419 you find evidence for dual nucleus. NGC 4473 appears to be a previously unknown dual nucleus. And here are the separations for all of the 3. And now we come to the second project. The second project is on a particular quasar, E1821 plus 643. This is a radium quiet quasar of redshift only about 0.3. It also has a huge extended emission region. There has been previous work on spectropolarimetry for this quasar done by, again, my advisor, Robinson et al., 2010, where they found that in total and polarized light, Doppler shift were observed between the H alpha and the narrow line region. In the total light, as you can see here, the H alpha appears to be red shifted with respect to the narrow lines, and there is an extended red wing. In polarized light, however, you see a blue shift and an extended blue wing. This was also modeled in 2 different components for 2 different velocities by Robinson et al. The theory behind this was that the black hole is moving towards a scattering screen, which is why you see a reversal of the shift when you observe it in total versus polarized light, because you see the light that is reflected from or scattered from the scattering screen as it is coming. So now's the question, what exactly is happening in this galaxy? Is this a candidate recoil galaxy, or is it just some of the lines that are displaced or have a Doppler shift? To further study this, spectroastrometry was conducted on this galaxy. Spectroastrometry is a technique to measure the relative spatial displacements across spectral features in a 2-dimensional spectrum, such as a long slit spectrum. This is done by measuring the centroid of the light profile along the slit at each wavelength. Any spatial asymmetry that coincides with a spectral feature, such as an emission line, will tend to shift the centroid to its adjoining wavelengths. And here are the results that you see from the Gemini observations. Here is the 2-dimensional spectrum showing the region of H beta and the 2 oxygen lines here. On the top here is a spectrum, again showing those 3 emission lines. This particular 2-dimensional spectra was in the north-south direction, the results of which are over here, where you see that there is an offset in the oxygen 3 lines. A similar offset was also found in the west-east direction, in particular in the west direction, for the 2 oxygen lines. The displacement was about 40 to 60 milliards seconds. And the total direction, of course, is northwest. Here, the top row shows the zoomed-in offsets for the north-south and the west-east directions for the 2 oxygen 3 lines. The 2 bottom panels over here show the flux, again, zoomed in from the previous plot. The offsets, north-south, are plotted against the west-east offsets here, which we get a total offset of about 90 milliards seconds in both the north-south and the west-east direction. The mu in this table is the measured offset, and the d is the continuum corrected offset. So, now that we have a displacement in the oxygen 3 lines, we need to know more about the oxygen 3 emission, which is why we also obtained Hubble Space Telescope images for the oxygen 3 emission in order to study it. We've obtained images in the continuum, oxygen 3, and H beta. As you can see here, you can see extended oxygen 3 emission, but we also need to know the morphology of the oxygen 3 in the central region. As you can see again, the quasar is really bright and dominant, which means in order to study the morphology, we need to subtract the light of the quasar. This has been done by 2 different methods, one of which is shown here, the manual subtraction. Here is the original image. The middle panel is a standard star obtained in the same ramp filter as this image was taken. The star is then scaled to the original image, and here we have the residual, which shows that there is an intrinsic asymmetry in the oxygen 3 emission. The same analysis was also conducted using Galfit modeling, and we obtained a very similar result, which means that the oxygen 3 emission is indeed intrinsically asymmetric. But now we have another question. Does this asymmetry account for all of the displacement that we see in the Gemini observations? So, For this, we performed spectroastrometric simulations. For the simulations, a three-dimensional array was created by combining the Hubble Space Telescope oxygen 3 image with the Gemini spectra, where the third dimension is the wavelength. Each pixel of this image is then assigned one of the spectra, which is scaled to the pixel flux. This data cube is then also convolved with a Gaussian profile which represents the typical scene conditions for Gemini to mimic ground-based observations. And just as in the Gemini observations, we simulated a two-dimensional long-slit spectrum from this in both the north-south and the west-east direction as in the Gemini observations. Spectroastrometric measurements were then performed just as those by fitting Gaussians along the spatial direction for each wavelength. For the purposes of this simulation, for the very central nuclear region, we used an oxygen-3 subtracted spectrum, but we also included the amount of oxygen-3 that the quasar would account for in the central region. For the second region, we chose a region that encompassed most of the extended oxygen-3 emission, and we used the oxygen flux. For the remainder, we used the extended spectrum. And here are the results. So on the top panel for each of the two sets of plots are the spectrum, and then the other two show the offset in the north-south and the west-east direction. As against the Gemini observations, these are much less than the ones that Gemini observed. These are only between 5 and 9 milliarc seconds, which are much less compared to the 90 milliarc seconds we got from the Gemini observations. Which means that oxygen-3 does not correspond to all of the observed displacement that we see in the Gemini data. So to summarize all of the conclusions for this quasar, spectropolarimetry shows that there is a Doppler shift between the broad lines with a velocity of about 2,000 kilometers per second. Gemini spectroastrometry shows that there is a displacement in the oxygen-3 lines of about 90 milliarc seconds in the northwest direction. The Hubble Space Telescope image analysis shows that the oxygen-3 emission is indeed asymmetric in approximately the east to north to west direction, which was the bulk of the asymmetry. And as I had shown before, there is a secondary arc in the northeast to north direction, which goes to about 5 kiloparsecs. However, the spectroastrometry simulations reveal that the contribution of the oxygen-3 emission is only about a fourth, 25% of what we see in the Gemini observations. What this means is that recoil hypothesis still remains a compelling argument to explain to explain the observed displacement. So, to conclude both of the projects, or to summarize both of the projects, in Project 1, out of 96 galaxies that we analyzed, robust candidates were obtained for 6 different galaxies, out of which 5 were in core elliptical galaxies, and only 1 was obtained in a power law galaxy. Out of the 5, 2 of them showed displacements approximately in the direction of the jet axis, which means that asymmetric jet power could be a possible cause for the spatial offset. We also found 3 dual nuclei, out of which 1 was previously unknown, and I hope to study them in the future. And we also see that preferential displacement was found in core elliptical galaxies as against in power law galaxies. Again, that was expected, so yay! In the second project, spectroastrometry showed about 40 to 60 milliarc second and up to 90 once it was continued corrected in the oxygen-3 lines. And the HST image analysis shows that there is an intrinsic asymmetry in the oxygen-3 emission. However, spectroastrometry simulations reveal that the oxygen-3 emission accounts only for about 25% of the observed displacement, meaning that the recoil hypothesis still is a big contender. So there is relevance to galaxy evolution. Once confirmed all of these galaxies, understanding the incidence of the recoil candidates that I have mentioned before, we can get a better understanding of galaxy evolution. We can put better constraints on supermassive black hole merger rates as well as galaxy merger rates. By performing Monte Carlo simulations, we can obtain the incidence of these recoils and what we expect to see, just as what Lena did in 2014. We can also identify more recoil candidates to get a better analysis, because we only identify 96. Let's go to more. JWST will give us a resolution about 3 times better than that of HST in the infrared, which I can use to further confirm my candidates. We can also expand the sample by cross-matching the X-ray observations with currently available high-resolution images in order to expand our sample and further test how many recoils we can find in the universe. So once confirmed, these recoil candidates are signposts of supermassive black hole binary mergers, which are sources of very strong and very luminous gravitational waves. Unfortunately, these lie outside the range of the ones that can be detected by LIGO. So until LISA comes online, we have to rely on different methods. But we can also provide empirical data for LISA. Once we get an incidence of how many that we see in the universe, it can provide an empirical data point for future LISA observations. We can also characterize the different properties of the host galaxies in which we see these recoils, which can help in understanding galaxy evolution better. So, until LISA comes online and gives us gravitational wave observations for supermassive black hole binary mergers, I shall keep chasing my monsters on the move. Thank you.
So now we have some time for questions from the audience. Jen?
So you focus on elliptical galaxies. Could you use some of the methods that you were just applying and some of these future methods to look at spirals?
So the reason why we focused on elliptical galaxies was mainly due to the morphology of the galaxies. The method that we are using to do the isophotal analysis would not work very well with spiral galaxies due to the morphology being uncertain, and in particular, the isophotal twisting would be very heavy in there, as well as dust obscuration. So we can't use this particular method. But if we can get a perfect position, say for the X-ray position, and we can get another way to find out the photocenter, we can still use spatial offsets in those. But we're using elliptical galaxies for another main reason, which is that elliptical galaxies are formed after galactic mergers. So if there is a galaxy, a spiral galaxy that somehow is formed after galactic merger, we could look at that, but mostly they go into ellipticals, and that's our main motivation for elliptical galaxies.
Yash, your summary plot of the ensemble of measurements with
Should I go back to that?
yeah, if you don't mind,
Which one?
the one that shows all the optical and infrared offsets as a function of redshift, I think.
This one? Yes.
So how many objects do you have both infrared and optical offsets for?
18.
And is there?
Actually, we have infrared and optical offsets for the entire sample. I'm showing the 18 candidates over here. Sorry.
Okay. And is it consistent for both of them? You showed one example where they're going off in the same direction.
Yes.
Always consistent.
For the robust candidates, they are. So not for all of the 18, which is why in my final sample, half of them are each other.
And is there a trend where the optical is always larger than the?
Yes, so in general, the optical is more affected by dust features, which is what causes a lot of the uncertainties in the isophotal analysis, which is why a lot of times the optical is larger than the infrared observation. Another reason is that if there is a central dust plane, the center of the AGN is also affected by that. So actually, just in the case of the one that I showed before, it affects where the exact position of the AGN is, which is why you get a larger offset in the optical than the infrared.
Victoria, you said.
I didn't think of it in the question, but you guys didn't have any X-ray measurements.
We did not.
Would that help?
Yes.
Because it would probably be a lot easier to get through the dust problem.
Yes. So the reason why we chose the same image for both was to avoid the error that comes in taking two different scales and then combining them. The errors that we're looking for and the displacements that we're looking for are small enough in this particular sample that having X-ray observations and then just the error in converting what that position is to the corresponding position on our images would be approximately the displacements that we want to observe or that we expect.
So you mentioned that the dynamical friction is due to this free body interaction, is that correct?
No, so dynamical friction is just due to everything else in the galaxy. The three-body interactions are mostly with the stars in the galaxy, in the center of the galaxy. So it causes just three-body interactions where the third one, the star, is chucked out of the system, and then that causes the binary to decay due to angular momentum being taken away by the star.
I see. So the core galaxies, do they rotate, the center of the galaxy, the core rotate almost a solid body?
The bound system, yes. So the supermassive black hole binary becomes a bound system in the center. So
I mean, the
That-
entire, all of the entire structure is rotating more or less as a solid, as
More or
opposed
less.
to a Keplerian type of.
yeah,
Whereas the power law is,
the power law are just other galaxies where you've not expected a binary to form.
how
in
do
it.
they
So
rotate? How does the center of that galaxy rotate?
I am not
Is it
exactly
more
sure.
Keplerian or is it?
It would have to depend on the initial circumstances that lead into that particular elliptical, but yeah, I'm sorry.
Okay, well, my fascination is that many rotating systems, the cores are rotated as a solid body. And then they behave somewhat differently outside of that.
Okay.
Forget about missing matter and all that other kind of stuff. But so in a fluid, it's because of viscosity.
Right.
And so I imagine that at least it should be analogous to what happens here. So
Mhm.
you have this displaced black hole kind of in a viscous kind of
Yeah.
model.
Yeah.
So you said it can go up to 100 parsecs.
Right.
But you haven't told us the period. Is it actually, you expect it to oscillate through the center of the galaxy,
Yeah.
around and
Through
complicated
the
fashion?
center of the galaxy usually.
Why? Because it seems like it'd be all 3 dimensions and all kinds of crazy.
I mean, it depends on where the initial kick is, in which
Yeah.
direction the initial kick is, and then that can
So how
cause it
important
to
is
oscillate.
it? Well, first of all, how many oscillations do you expect in 1 billion years?
That again depends on the initial conditions, like what the mass ratio of the
Typically.
black holes and
What's a Q, basically?
I'm honestly not sure. But I mean, 1,000 kilometers per second, 1 billion years, few kiloparsecs. I'm sorry, I could calculate that, but I don't know the number.
Okay, and it's curious because again, if it's damp, in
Yes,
some
it is
sense,
that.
then you might expect it to be quite different than if it's
Yes.
maybe a power law that might end up able to be more
Yes,
dynamic.
so if I just go back to the merit simulation that they did, I mean, in this particular case, it was gas. So in this particular case, that is why the phase 1 oscillations, the one that can have even larger amplitudes, are very quickly damped because there's that friction.
Okay, but then, so then in this, what you're showing now is the phase 2?
And yeah, that was the phase 2, and then
And
it just
it doesn't look
settles into the
viscous at
phase.
all here, so is that?
In this particular case, it was a no gas dry merger.
Just antibodies.
Yeah.
Okay, everything's
stand
going
by,
on.
yes.
Okay, okay, gotcha. All right, thank you.
Yes.
Yeah, so since you're using visual methods to observe the offsets of the AGNs, and since it is going to be an oscillation, you'd expect that at some point in the various lives, you're going to get the black hole back roughly in the center of the galaxy. How do you think that would affect the numbers that you see?
That's actually a very good question. So we actually expect the black hole to spend a lot of its time in the oscillation. So Black et al. Have discussed this the probability of finding the black hole at different points in its oscillation. But yes, that is a bias that comes into place where you can't really tell how much time has elapsed since the coalescence. So if you happen to look at a galaxy which has a recoiling black hole, well, the spatial method wouldn't quite work in there. Velocity method, on the other hand, will work in there.
So, if no further questions, I think it's probably time to move into the closed session.
I think that would announcement.
In the closed session, right? That's what I was saying. Yeah. So, let's thank Josh again. And so everyone is not Josh will finish it. Dismiss now.
I'm using a favor check the lists for like every day except yesterday. I haven't done it yet. Correct. Okay, sure. Realize there's still meetings
Well, in the phase 1, even though it's collision, it's still creates.